Every single time you send an email, stream a movie, or just browse a website, you're actually relying on an invisible structure. It's like a hidden map that's guiding all your data. So today, we're going to decode those maps. We're diving into the hidden blueprints that dictate how our entire digital world is built, and it all starts with a really basic question. And you know what? That's a great question. We just take it for granted that our devices connect, right? But it's definitely not magic. Behind every single stable, fast network is a very deliberate design, a blueprint that decides not just if devices can talk, but how efficiently and how reliably they do it. And that blueprint has a name: network topology. At its absolute core, it's just the physical or logical layout of all the stuff in a network. Think of it as the architecture for our digital spaces. And this arrangement, well, it's the foundation for everything. It determines a network speed, its resilience, and even how much it costs to build. So here's how we're going to break it all down. First, we'll look at why we arrange networks in certain ways. Then we'll check out some classic and modern designs, uncover a fascinating twist between how things look versus how they actually work, and then we'll wrap it all up with why any of this actually matters to you. Okay, so arranging a network isn't just about plugging in a bunch of cables and hoping for the best. Nope. It's a strategic balancing act. Every single design choice you make is a trade-off between three really key things: how much it costs, how reliable it needs to be, and the physical, real-world geography you're dealing with. So let's see how those principles actually played out. We're going to start by looking at some of the classic blueprints. These are the old-school, foundational designs that really paved the way for the networks we all use today. First up is the bus topology. I want you to picture a single main highway, or what they used to call a backbone. This was the go-to design for the very first Ethernet networks. Every single computer, every printer, everything on the network connected directly to this one shared cable. So what was the big appeal? Well, it was super simple and really cheap. You just needed one long cable, and you were basically done. But that simplicity hid a massive, massive vulnerability. If you got a single break anywhere in that backbone cable, the entire network would just collapse. It was a huge single point of failure that made it incredibly fragile. Next up, we've got the ring topology. Now, you're not going to see this much in modern offices, but it was a really key design for older standards like token ring. In this setup, instead of a single backbone, data traveled in a continuous loop, getting passed from one device to the next, kind of like passing a note around a circle in class. So how did they fix that single point of failure problem? Well, engineers came up with a really clever solution: the dual ring. For supercritical fiber networks, they would lay a second, totally separate backup ring. If the main path ever broke, bam, traffic would instantly switch over to the secondary ring. It was a brilliant, self-healing design for its time. All right, enough with the history lesson. Let's jump from the classics into the present day. These are the workhorse designs that form the backbone of pretty much every network you and I interact with on a daily basis. And this one is quite literally the star of the show. The star topology is, without a doubt, the most common layout you're going to encounter out there. Just think about your home Wi-Fi router. That little box is the center of your very own personal star network. The huge advantage here is resilience. If the cable going to your laptop breaks, only your laptop loses its connection. Everyone else in the house is totally fine. It isolates failures beautifully. But the star has its own Achilles heel. If that central hub or switch dies, the entire network goes down with it. But what if you absolutely, positively cannot have your network go down? What if downtime is just not an option? Well, for those critical connections, like the massive links that connect different parts of the internet, you need a mesh topology. This is the design for maximum over-the-top reliability. Now, the reason a full mesh is so incredibly reliable is actually pretty simple. Every single device is connected directly to every other device. This creates a ton of redundant paths for data to travel. But as you can imagine, the number of cables and the cost, it just skyrockets. It's the gold standard for uptime for sure, but man, does it cost a pretty penny. Okay, so since a full mesh costs an arm and a leg, most real-world mesh networks use what's called a partial mesh. And it's a really practical compromise. You still get multiple, redundant paths for all your data, but you're not connecting every single device to every other one. Your data might have to hop through another router to get where it's going, but you keep that high reliability without the insane cost. Now let's look at something you see all the time in the corporate world. For big companies with a central headquarters and lots of smaller branch offices, the hub and spoke model is a classic. It's a really smart way to manage the super high cost of those wide area network or WAN connections, the expensive links that connect distant locations. So here's the game plan. You put a big, powerful, beefy router at the central hub. That's headquarters. Then, all the smaller, remote offices, the spokes, connect directly back to that central point. All traffic has to flow through HQ. It's a very practical, centralized design that's been a go-to for decades.
All right, so we've looked at all these different blueprints, but here is where things get really, really interesting. Because when you look at a network, what you see isn't always what you get.
So let me ask you this. If you see a bunch of computers all plugged into a central box, can you be absolutely sure you know how the data is flowing between them? The answer, which might surprise you, is no, not at all.
And this brings us to one of the coolest concepts in networking, the difference between a network's physical topology and its logical topology. The physical topology is what you can literally see and touch, the actual layout of the cables and devices. But the logical topology, that's how the data actually moves. It's the path the information takes, no matter what the physical wiring looks like.
This quote from our source material just says it perfectly. The physical topology is what you can see, and the logical topology is what the network can see. A perfect example was that old token ring technology. To your eye, it looked like a star with all the cables running to a central box. But logically, inside that box, the data was being passed from port to port in a perfect circle, a logical ring hiding inside a physical star. So we've covered a lot of ground here, from old school designs to the difference between sight and reality. But why does any of this matter? Why is it important to understand these invisible blueprints in our everyday lives? Let's wrap it all up. So if you only remember 3 things from all this, make it these. First, every network design is a trade-off, a careful balance between cost and reliability. Second, the star topology is the king right now. It's the design you'll see almost everywhere. And maybe most importantly, what you see isn't always the full story. The logical path the data takes is the true map of the network. So I want to leave you with this thought. The next time you connect to the Wi-Fi at a coffee shop or at the office or even just sitting on your couch at home, take a second. Think about that hidden structure that's working just beneath your fingertips. What invisible map is your data following right now to bring the entire digital world to you?